So I see that some kids have been doing this in the classroom, and I've got a little printout with some of the results here. Okay, so you guys have cut up squares, and that similar to how it came out for me. That's good. So somebody here even dissected the square into triangular regions and got the triangles to add up a half, a quarter, an eighth. Oh, that's excellent. That's very beautiful as well. And I think it's nice to have a project here where you can just sort of feel free to play and put things together in more than one possible way. And it looks like some really nice work here with the both in terms of how you put it together graphically, and then make some stories and songs, and really get to get your money's worth out of this particular project. In university level mathematics, of course, it's not so far off. This particular topic is pretty interesting because it touches on something that you end up doing when you want to solve a problem like this here. I'll try to make a drawing that is visible to the camera. So I've got some curvy line and some supposedly straight lines here. Now, doing what we were doing, we know how to work out areas of regions that are bounded by straight lines, but one thing that comes up in nature, of course, is to try to work out, a numerical value for what the area is of a region that's bounded by a curvy line. And one of the first things you say is, well, I don't know how to do it. But then if you study calculus, one of the first things that you do in calculus is to try to solve this problem by approximating, say, the area of this region under the curvy line. Just figuring out, if this is a lawn, how much grass did we have to plant? Well, if you want to estimate it, and you're not good at curvy lines, then the traditional thing, old trick, is to cut it into rectangles and then measure up the rectangles. If you know that these are all, 1 step wide, they don't look like it, but they're supposed to be. If they're all equally spaced, then I just measure the length, and I could add up the areas of these rectangles, and I'd have almost the area of the lawn bounded by the curvy line, but not really. So then you'd say, well, okay, a better estimate would be to take rectangles that are only half as big, and I won't actually draw the rectangles because it's too fiddly with my picture here, but I'll just subdivide twice as fine. So then I get these, well, I'll draw some rectangles. So the key is that if I make my strips skinnier, then I get something that's total area is actually a lot closer to what's under the curve. And then if you could imagine, here's where you can imagine, and I can't draw, really, really skinny strips so that their tops don't have a little much of a tooth sticking out, so that the strips are basically a very close approximation to the region. Then, well, I never quite get the exact region with the curvy line, but I get closer and closer by approximations that get finer and finer. And then the same process of making sense. Well, what does it mean to say, well, what do you get if you actually take the strips to be smaller and smaller? Does the area behave nicely? Does it get closer and closer to a single number like it did when we were adding up fractions? And then, well, often the answer is yes. Like for this problem, the answer is yes. And you say, well, that's what we mean by the area under the curvy region. And we can work it out by one of these processes where at no step do you have exactly the right answer, but the limit as you take your strips to infinity gives you the thing you're looking for exactly. And so you see that in calculus, in theory of integration, and a very fundamental thing, and you guys are doing it here already, so it's somehow a basic thing as well. So then if we compare what you've been doing with this dissection of the square into pieces that shrink by a half at each step, of course these pieces never filled the whole square. No finitely many collection of pieces could do that, there was always a little error left over. But as you took more and more pieces, you got closer and closer to having a sum of fractions that added up to 1. And so the same argument that we're sort of seeing, well, intuitively these guys fill the square if you're allowed infinitely many pieces. Over here in calculus, you say, well, if I want to work out the area of this curvy region, then no approximation by cutting up little strips and pasting them over it is actually going to give me the right answer. But then maybe by some thinking you could say it gets closer and closer to some number as I make my strips skinnier and skinnier. And that's the same process that you were doing here. You're taking a limit as the number of terms goes to infinity, or as your approximation to the square gets better and better by having more and more terms. So what you're doing here is really what you're doing here is completely the same as what you're doing when you compute an integral in integral calculus. So this process of taking a limit, which you did here, is also what you do here, and somehow that's one of the core ideas in calculus, keeping the handle on infinity in this way